Ever pondered why things fall down and not up? Or why we're not floating off into space right now? These are the kind of questions that leave us scratching our heads, wondering about the intricate mechanisms that govern our universe. Today, we're going to delve into one such mechanism, gravity. Gravity, in essence, is an invisible force that pulls two objects toward each other. It's like a silent, unseen puppet master, controlling everything from the fall of an apple to the orbits of planets. It's the reason you're sitting in your chair right now and not floating around your room. Now, you might be wondering, how does gravity work? Well, think of it like magnets. Magnets have a natural attraction to each other, right? The closer they are, the stronger the pull. Similarly, every object in the universe, no matter how big or small, exerts a gravitational pull on every other object. This attraction is dependent on two things: the mass of the objects and the distance between them. The greater the mass, or the closer the objects, the stronger the gravitational pull. Consider the Earth and a tiny pebble. The Earth, being massively larger, exerts a much stronger gravitational pull, which is why the pebble falls to the ground and not the other way around. Similarly, the Earth is held in its orbit around the Sun due to the Sun's much greater gravitational pull. But here's something to blow your mind. We're also pulling on the Earth and the Sun with our own gravitational force. Yes, even you sitting there are exerting a gravitational pull on everything around you. However, since our individual masses are so small compared to these celestial bodies, our pull is practically negligible. So in a nutshell, gravity is the cosmic glue that keeps everything in place. It's the reason the universe functions the way it does, from the motion of galaxies to the fall of an apple from a tree. So thanks to gravity, we're all grounded, quite literally. Ever wondered why you weigh less on the moon than on Earth? Well, let's dive into the fascinating world of gravity to unravel this mystery. Enter Sir Isaac Newton, the man behind the law of universal gravitation. In the late 17th century, Newton proposed that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Sounds complicated, doesn't it? Don't worry, let's break this down. Imagine a trampoline. Now place a bowling ball in the center. The bowling ball would sink into the trampoline, creating a dip. This dip represents the gravitational field of the bowling ball. The larger the object, the deeper the dip, and the stronger the gravitational pull. That's why Earth, being larger and more massive than the Moon, pulls you towards it with a much greater force, making you weigh more. The law of universal gravitation explains why planets orbit around the Sun, why the Moon orbits around the Earth, and why we don't float off into space. It's the invisible string that holds the universe together. But what about the distance factor? Well, the farther you are from the center of an object, the weaker the gravitational pull. Think about the trampoline again. The dip is deepest, closest to the bowling ball, and gradually becomes shallower as you move farther away. This is why astronauts experience weightlessness when they're in orbit. They're far enough from Earth that its gravitational pull is significantly weaker. To sum it up, your weight isn't determined solely by how much you eat or exercise. It's also influenced by the mass of the planet you're standing on and your distance from its center. Gravity, it turns out, is a cosmic game of tug-of-war. So your weight isn't just about your love for pizza. It's also about where you're standing in the universe. What if we told you gravity can bend time? Sounds like a sci-fi movie, right? Well, hold on to your hats, because we're about to dive into one of the most fascinating aspects of modern physics: time dilation and gravity's role in it. Imagine you're on a train, zooming along at near light speeds. Don't worry about the practicalities. This is a thought experiment after all. Now, you're sitting in your compartment, casually bouncing a ball. To you, the ball just goes up and down, a simple, vertical path. But to an observer standing still outside the train, the ball's path isn't just vertical, it's diagonal. Because as the ball moves up and down, the train, and you and the ball, are all moving forward. Now let's replace the ball with a beam of light. Light, as you may know, travels at a constant speed. Unlike the ball, it can't speed up when the train moves forward. So, to the observer outside, the light beam takes a diagonal path, just like the ball. It travels a longer path than it would if the train were stationary. But here's the kicker. Since the speed of light is constant, and it's covering a greater distance, It must take longer to complete its journey. So from the observer's perspective, time on the train appears to slow down. This is what we call time dilation. Now, what does this have to do with gravity? Well, according to Einstein's theory of general relativity, gravity isn't just a force. It's a warp in the fabric of space-time caused by mass. A massive object like our Earth distorts space-time around it, much like a bowling ball on a trampoline. This distortion affects the path of light, causing it to follow a curved trajectory. And just like in our train analogy, this longer path means time appears to slow down in a strong gravitational field. So, next time you're late, just blame it on gravity's effect on time. Gravity doesn't just keep us on the ground, it shapes our lives and our world in many ways. Let's delve deeper into the effects of gravity, starting with the most visible one, the tides. Ever noticed how the sea has a rhythm, how the water rises and falls predictably every day? This is due to the gravitational pull of the moon and the sun, tugging on the Earth's water and creating this ebb and flow we know as tides. Now let's get a bit more personal. Have you ever thought about why we're built the way we are? Why our bones are sturdy and our muscles strong? Gravity, again, plays a crucial role. The force of gravity has shaped our physical evolution, requiring us to develop strong bones and muscles to resist its pull and move around. The same principle applies to all terrestrial life forms, from the tiniest insect to the tallest giraffe. Even plants aren't immune to gravity's influence. It guides their growth, a phenomenon known as gravitropism. Simply put, roots grow downwards into the soil, following gravity's pull, while shoots reach upwards against gravity towards the light. Let's think of the Earth as a water balloon for a moment. If you hold a filled water balloon by its top end, it will stretch and bulge at the bottom due to gravity. In a similar way, gravity pulls everything towards the center, which is why planets, including Earth, are round. If gravity was stronger, our planet might be even more compact, while weaker gravity could result in a more spread out, less spherical shape. So you see, gravity isn't just about keeping our feet on the ground. It's constantly at work, shaping the rhythms of our oceans, the structures of our bodies, the growth of our plants, and even the shape of our planet. So, gravity isn't just a force, it's a sculptor, shaping and molding everything around us. So, we've talked about what gravity does, but what exactly is gravity? This question has been puzzling scientists for centuries. Today, we have a better understanding of gravity than ever before, but there are still many mysteries left to unravel. Our current understanding of gravity is largely based on Einstein's theory of relativity. According to Einstein, gravity isn't a force that pulls objects towards each other, as Newton suggested. Instead, it's a result of the curvature of space-time caused by mass and energy. This might sound a bit complicated, but let's use a simple analogy to understand it better. Imagine you have a rubber sheet stretched out flat. This sheet represents space-time. Now, place a heavy ball in the middle of the sheet. The ball causes the sheet to curve downward. If you were to roll a smaller ball along the sheet, it would naturally move towards the heavier ball. Not because the heavier ball is pulling it, but because the path it follows, the rubber sheet, is curved. In this analogy, the heavy ball is a massive object like the Earth, and the smaller ball is something with less mass, like an apple falling from a tree. But the story doesn't end here. Scientists are currently trying to reconcile Einstein's theory of relativity with quantum mechanics, the theory that explains the behavior of particles on the smallest scales. Some believe that to fully understand gravity, we need to find a way to unite these two theories into a single framework. This is one of the biggest unsolved mysteries in physics today. Gravity, then, is this incredible, invisible artist, constantly shaping the universe and our place in it. It's a force, or rather an effect, that we can't see, but we can certainly feel. It keeps our feet on the ground, governs the motion of planets, and even bends light. And while we've come a long way in our understanding of gravity, there's still so much more to learn and discover. So let's keep exploring, keep digging deeper, and keep marveling at the wonders of our universe.